Welcome you all here today. We're going to start this is the second installment on the Freeway Facilities Procedure training. This is a workshop, but it's a training workshop. And it's not one where it's a static deal where the presentation's all been set in stone. In fact, this is kind of an experiment. It's a dynamic experiment, and we expect and encourage participation from you. If you have questions, ask them. It's a lot easier to get the answers now than it is to wait and perhaps forget what the question was about. So this is the second installment, and then in the annual meeting in January, we'll have a third installment where we'll get into more details. The first installment was the webinar. I think some of you were in attendance there. That was a few weeks ago. And there we talked about the basic organization or steps of the procedure or methodology. And today we're going to get into more details in terms of talking about specific equations, but yet we're not going to get down to calculations. As you can see here, we've got some representations of equations. We'll talk about specific examples of freeway segments, what happens there when certain conditions exist. And then in the annual meeting, we'll get to more specifics, where we'll actually go through examples and apply numbers to the equations. And hopefully, through all this process, it'll bring up questions that you have, answers, better understanding. The idea here is to elevate the understanding of people interested in freeway facilities, wanting to take part in the Freeway Facilities and Multi-Lane Highways Subcommittee. With that in mind, go ahead and start off here and hand the mic over.
Okay. Thank you, Mike. Okay. But I can't use it. Okay, well, so as Mike said, this is going to be an experiment. Roger, if you could get the hydrochloric acid that we ordered, and we're all set up, perfect room for it. So, the intent again is to provide an overview of freeway facilities, and specifically the oversaturated methodology that has been in the HCM ever since the 2000 manual, but I would say, is probably not as well understood as it should be. And as we're looking ahead at HCM 2015 or major update, I don't know if there's a year really. There's no year in the RFPs. I don't know if that's a hint in any way. What we're trying to achieve is a better understanding of this methodology, because one of the key charges, obviously, for the committee is to identify knowledge gaps, identify improvement needs, and really the best way to do that is to first understand what's currently in there. And so I think we have a pretty varying level of experience with the methodology here. It's a committee-wide workshop. And I know the Signals group is going to pay us back in a couple hours where we have to listen to their stuff. So, but we'll make the best of it. So I'm going to start with a little bit of an introduction here, and then I'll hand it over to Scott, and we'll kind of tag team. And again, this is supposed to be really interactive. And if you have pen and paper, pull it out. Some of these facilities, you can sketch them out, some of these examples, and then you'll have them to refer back to. So chapter 10 is the facilities chapter. It's the chapter that combines the basic segments, the weaving segments, and the merge and diverge segments into a facility context of several miles, 10 miles, 11 miles, maybe longer than that, and also does that over multiple time periods. And that goes back all the way to the 2000 manual, where this methodology had the extended time-space domain, where we can look at up to 6 hours in the current computational engine implementation for these facilities, and we can look at queues growing and dissipating. And so really, on the undersaturated side, this methodology is nothing terribly exciting. It's just aggregation. It's adding up numbers and doing a weighted average and so forth. We're not going to spend a whole lot of time on that. But the oversaturated is kind of a key one to understand, and it's especially important as we're talking about reliability, because one of the key motivations, from my perspective, for the HCM major update project is to incorporate all the results from LO8, the reliability work, into the manual. And this methodology, Freeway Facilities, is the seed file. You can't do reliability for freeways without doing this methodology. And so even if you're not doing, freeway facility analysis, if you're doing freeway reliability, you'll have to go through this process for the seed file, and then we do all the variability in demand and capacity and incidence and rain and weather and so forth. But the core engine did not change significantly in LO8. There were some minor improvements, some minor changes to capacity implementation and so forth, but really the concept is the same thing that we had in the 2000s. And the methodology is relatively straightforward when you read Chapter 10. It gets slightly more complicated when you read Chapter 25, which is the supplemental chapter. But in Chapter 10, it's a pretty easy method with you gather input, you adjust your demands, so the input includes the geometry and includes your traffic volumes, your truck percentages. You adjust those demands to then, do your passenger car equivalents and so forth. You estimate segment capacities for all your segments. You can adjust those capacities for incidents, for rain, for weather, work zones, and so forth. That really, step 4, is the key piece of LO8, adjusting those capacity to represent impacts of non-recurring congestion. You then look at your D over C ratios across all the segments along your facility, and then that's where it gets interesting. If everything is under capacity, if all D over C ratios are less than 1, it's a simple aggregation. But if any segment is over capacity, you go into the step 6B, this highlighted box here, and that's the one that then really gets very, very complicated. And really what we're hoping to do today is illuminate a little bit of what's going on inside step 6B, which is described in a lot of detail in Chapter 25. So that's what we'll talk about. And then the last step is just, again, estimating the overall density and level of service. So what is this oversaturation model? You have two primary causes for congestion. You could have congestion either caused by excess demand or by a reduction in capacity or by some combination. All right, so if you have fixed facility, yes, sir, please, it's interactive.
It's interactive. Can you get kicked into the oversaturation model if you just have a ramp merge problem?
If you have a ramp merge problem, it will depend. It depends on whether it's only the ramp that's over capacity or whether it's the main line that's also over capacity. But if the procedure in Chapter 13, if the ramp influence area is over capacity, it's essentially looking for any D over C greater than 1. So yes, if the main line fails in the ramp segment, then it will be invoked.
D over C greater than 1 across all lanes. It could be the two right lanes. Okay, great.
Yeah. However, it will not be invoked if it's just the on-ramp, and that's the discussion we had at the webinar, that if it's only the on-ramp that's oversaturated, but the main line itself is undersaturated, then you just have really long queues on the ramp, but you don't have any mainline queuing. That's debatable whether that's true, but that's the way it's currently implemented. So this procedure starts if any segment has D over C greater than 1, and what happens is that these calculations are done in very short, discrete time steps, and what I've called here a modified cell transmission approach. And that's really the key to understanding this methodology. And it allows you to handle front clearing queues and back clearing queues. Back clearing queues is your standard congestion where you have a bottleneck, you have demand that increases, capacity is fixed, the demand drops, and then the queue slowly clears from the back. The front clearing queue is one that happens as a result of an incident. When you have a relatively fixed demand, for example, you have a temporary drop in capacity due to the incident is resolved, and then the queue clears from the front. Both of these are within Chapter 10, but they're implemented slightly differently, and we'll talk about what those differences are. So what I mean by this modified cell transmission approach, and I think this is one of the biggest areas of confusion in this chapter, that there's a diagram that talks about shock wave, and it talks about the Gonzo cell transmission model, but what are we actually doing here? Gonzo introduced basically this macroscopic simulation model sometime in the mid-90s that basically takes a facility and divides it into short segments and into short time step, and then basically models on a macroscopic level flow moving from one cell into the next cell. And that flow is limited by certain flow constraints, which we'll go into a good amount of detail here in a second. it has nothing to do with microsimulation. There's no little vehicles moving around. It's not like CoreSim or vSim or any of those, but it's still a simulation where in every time step you check these various constraints, and based on those constraints, that basically predicts how much flow is processed across a node boundary in the next time step. How is this different from shockwave, which we all probably went through at some point in some entry-level graduate class or something like that? And it's very different in the sense that a shockwave is just an analytical estimate, if you will, of what the congestion regime is. And so we can't talk about freeways without having at least some speed flow or flow density regime. The shockwave model will just look at some upstream condition where this is flow, this is density, and then some condition in the queue within the bottleneck, and then you have a basically shock wave that describes the transition between those two regimes where the slope of that line is the speed of the shock wave. It's a very common principle in freeway theory, but it has nothing to do with what we're doing in FreeVal, or in the freeway facilities method. The only place where we're using shock waves is actually for the front clearing queues, which we'll go back a little bit later. But for the standard bottleneck analysis, for the standard back clearing queues, shockwave analysis is not used. Good.
Question of the shape of the curve.
Yes.
Your assumption, linear.
Right.
What's in that number right now?
Yeah. So I should probably elaborate. Currently, we have essentially a three-regime model to describe speed flow or flow density within freeway facilities. Anything capacity less than 45, if we look at basic segment, we have a linear portion here, which is basically the fixed free flow speed up until some break point. Then after that, we have some curved relationship up to capacity, and we have some new speed flow curves that were introduced with the HCM 2010. But so you essentially have one regime, here, where you have a linear relationship, then a curved relationship. And then once you exceed a density of 45 on the oversaturated, you do have a linear relationship. There's lots of research out there, though, that both from the US and internationally, that suggests some other shape of that curve, something that's, that may look something more like this. But this is what we currently have. Okay? So what does Chapter 10 do? What do we actually do? It's a hybrid model where we use a cell transmission-like approach, but we use HCM segments for the space separation. So rather than using de Ganzo's really short segments, we divide the segments up consistent with the definitions in Chapter 11, 12, and 13 into basic segment, weaving segment, merge, and diverge segments. But the time steps are still very, very short. So even though the HCM is based on 15-minute analysis, the iterations in oversaturated are actually being performed every 15 seconds. And so it is a macroscopic simulation model within the highway capacity manual, going back to the 2000, that estimates the rate, or it estimates queues building and dissipating over time. We do use the shock wave to estimate some impacts for front clearing queues based on this relationship that we just showed here. And we also use this speed flow relationship to actually estimate the density at the bottleneck and to get a sense of different flow constraints that we'll talk about more. What's really important in understanding this is this concept of nodes, and that's really sets up the discussion for the rest of the workshop. This mouse definitely doesn't work. Because essentially, while HCM chapters 11, 12, and 13 talk about, do I move around too much for you, Mike? While HCM chapters 11, 12, and 13 talk about segments, we actually do use nodes within chapter 10 to check those flow constraints. And so this is very different from a node on the interrupted flow side. This has nothing to do with a signalized intersection or a roundabout node or so forth. It's not a point analysis. We don't get performance measures for that point. But we use the concept of nodes to basically check how much traffic can actually move from segment 1 into segment 2. And we check that every time step. And so there is and these are exhibits directly out of Chapter 10 and Chapter 25. So the concept of an on-ramp node, of an off-ramp node, but really also two basic segments have a node in between at the boundary that checks demand coming in, capacity downstream, and how much traffic can actually go through. And so some of these terms here, the mainline flow, or MF, is actually the flow that can get processed through a node, but that flow is subject to a whole series of constraints. And those are summarized here. Essentially, what the simulation, the macroscopic simulation, checks every time step is whether the mainline input, or the demand, whether that can all get processed or whether it's constrained by one or more of these. And it can be constrained by the upstream capacity, it can be constrained by the downstream capacity. It can be constrained by the flow delivered from the upstream segment, because there might be a queue further upstream to where the actual flow arriving is less than whatever theoretical demand we put in. It can also be constrained by an on-ramp, where the mainline demand has to share capacity with the on-ramp, and there's certain algorithms that allocate capacity between the mainline and the on-ramp, and we refer to that as the MO1 constraint. It can also be constrained by any queue that happens in the downstream segment, where depending on what the severity of the queue is, depending on what the density is, there's some available storage capacity within that downstream link. And if that link is full, then traffic cannot proceed anymore. So that's very different from the DSC, the downstream capacity, which is a theoretical concept. The MO2 is constrained by actually a downstream segment being fully or partially queued. And then finally, an MO3 constraint as a function of incident and front clearing queues at an incidence. And so really the whole secret to this methodology is that each of these constraints are checked at every time step for every segment throughout the facility, and then it goes to the next time step, and then it goes to the next, and it goes to the next. And it does that every 15 seconds until you reach the end of the 15-minute time period. And it ultimately happens sequentially. The actual procedure is actually relatively linear, even though the flow chart, the real flow chart in Chapter 25 goes over, I think, 5 or 6 pages in the HCM. But the actual process is actually fairly linear. You initialize your segments with your base demand and capacities. You check off-ramp constraints. You get your mainline input or your demands. You then check for on-ramp constraints. You then calculate your actual mainline output. This is where all those, the mainline output constraints, MO1, MO2, MO3, where all those are applied. And then those translate to some sort of a mainline flow across the node. So the actual traffic processed across the node as a function of all those other constraints. And then that gets translated into a segment flow, and then that gets aggregated into facility performance measures. So it's a relatively straightforward process, but there are a lot of computations involved, and they're repeated many, many times. Lily? Yes. Exactly. Yeah, exactly. Yeah, the demand, all the inputs happen in 15 minutes, even though the calculations are performed in 15 seconds. And the reason that's done is that a segment may fill up to storage capacity within those 15 minutes. And there's actually output in the computational engine that tells you time interval or minute that queuing begins on a certain segment. So there is a discussion in, I believe, Chapter 25 on basically there's a trade-off between segment length and the time step. And basically, if you have time steps that are too long, you may get to the condition where a queue fills up more than one segment within that time step. So for example, if you have a 1,000-foot or a short, let's say a 300-foot segment, and you have a very long time step of a minute, and you have a queue, the red line, that shock wave, that grows at a rate that's faster than that segment, then you might get into a situation where the segment is basically over full, beyond jam density, before you can do the next iteration. And so with the 15 seconds, we can basically allow segment lengths going down to about 300 feet or so. It actually used to be back in the HCM 2000, when computers weren't quite as fast, it used to be, you used to have longer time steps to just allow the computations to go. But now we've gone down to 15 seconds to basically allow very short segment length. But that's ultimately the trade-off. You don't want a queue to fill up more than one segment in one time step.
But the 15 segment, you could go lower. It's a question of how long you want to wait.
You could, yeah. I mean, it's you could theoretically go down to 5 seconds or to 1 second. You know, then you're basically at micro simulation. David.
300 feet, the methodology becomes less reliable below.
If you have a very short segment of, say, 100 feet, and you have a very high, see, I knew I could use this. If you have a situation where you have a very short segment, and you have a very high upstream demand, and a very low downstream capacity, which is this is LO8, you know, written all over it. This is your incident within a heavy rain event or something like that. So you have very, very low capacity. The result is a very fast-moving shock wave. And basically, if that shock wave speed here, you know, whatever that rate of growth is, if that may fill up the segment beyond capacity. So while in theory that segment should be at whatever this density is, the algorithm doesn't compute it fast enough, and so you may end up with densities that are somewhere out here. And we've seen that in LO8 in some cases for other issues. But so theoretically it's possible with very high upstream demand, very low downstream capacity, and very short segments that you run into this issue where a segment fills up beyond jam density. So cars stacked vertically, basically.
If you go below 15 seconds, you can expect more accuracy under extreme conditions?
Yes. We had some other issues, or we identified some other issues in the code through LO8 that basically already fixed this. But that's in theory at least what could happen. I just broke your mic. Mike. I just won't use the clip. Okay, I'll just hold it.
It sounds like the 15 seconds is just something that's convenient for the purposes of the spreadsheet requirement methodology.
That's correct. And I don't know if there's any thought on going too low. I mean, if you go down to 0.1 seconds or something, I don't know if there's any other concerns that show up. But we know that our Excel implementation of the computational engine can be accelerated, and Scott has demonstrated that in his HCS implementation of the method. But with the reliability, we're still talking about running thousands of scenarios, and so going at a time step that's if you go from 15 seconds down to 5 seconds, and right now we're processing everything in 2 hours, you may run up to 6 hours. So that's just kind of the reality of it. Okay. Well, so this is the simplified flow chart. In reality, it looks like this. Thanks to Scott for taking 5 or 6 pages in Chapter 25 and fitting it on one PowerPoint slide. And we're not going to go through all these steps, but ultimately, this. Okay. So ultimately, this is nothing different from this. And maybe this should make its way into Chapter 25 in the next. That way maybe people will actually read it, because by the time you get to this, it kind of gets a little bit scary. Okay, so what we want to do, with however much, there's no clock in here, so you're at our mercy until somebody runs us out. What we're going to do for the rest of the workshop is really try and illustrate these flow constraints through some conceptual example problems that Scott had developed. And then really have an interactive discussion of which constraint governs. That's ultimately what we're trying to get at. So for these different conditions, what do you think is going to happen? If we can, in that process, identify limitations in our documentation, that'd be really great. So if you have read chapters 10 and 25, you're intimately familiar with them, and we're telling you something today that you've never heard of before, then that is a good indication that we need to add some text to it, whoever the contractor is for the next iteration. And if we can identify knowledge gaps and improvement needs, that would be great as well. And we'll keep track of all those. Okay? Any questions before we go to the hands-on? So if we can close the doors and...
Comprehensive flow chart, and it show you the equations and the equation numbers that come from Chapter 25 or Chapter 10. But again, the focus today is going to be a little more qualitative, not get into the real nitty-gritty of these equations. The plan kind of is that at the annual meeting, that hopefully we can work through a numerical example or two and really give you a full understanding of the quantitative aspects of this. But again, today the focus is more qualitative and to get into a little more discussion about some of these constraints that Bastian already introduced, MO1, MO2, and so on. And so I'm going to kind of step through this presentation that I have where we've got this more comprehensive flow chart and jump to kind of a breakout slide that deals with that section of the flow chart, kind of introduce the topic, and kind of turn it over to Bastian to expand on some of the topics. And also the plan is to use the whiteboard to show some simple geometric configurations that would apply to these particular concepts that we're talking about. And again, this is really informal. Anytime you have questions, just please jump on in.
Hey, Scott,
Yeah.
can we pause for a second? I want to check the sound
Sure.
on this. Okay.
Okay. All right. Ready? This slide here is just introducing some of the different variables that are used within the methodology here. And again, I don't really want to dwell on these, but we've got a lot of different variables in here that are being used with the procedure. And some of these will come up in the discussion today. And again, these are all enumerated in Chapter 25. And again, Bastian introduced the concept of the node, which is very important with this methodology. So we have a lot of variables that deal with the node. On-ramp variables. One thing that probably hasn't been mentioned yet is the RM ramp metering, and we can mention that later, is that might be a constraint to be concerned with as well at the on-ramp. We have off-ramp variables, the deficit condition we'll get into, we'll get a discussion about that as well. And then again, these got introduced in Bastian's presentation. So yeah, here's all the logic for this procedure, and this whole flow chart is contained within Chapter 25, just not as you see it here, because basically everything gets really small when you piece the whole thing together, and so it's presented in, I don't know, 5 or 6 different sections throughout Chapter 25. I managed, I think, to get a student to piece this whole thing together. And so you can see the whole logic from beginning to end. But again, it's so small you can't see anything that's going on there. And I'm going to go ahead and step through these different sections of the flow chart. The numbers are not necessarily identical to the numbers that you see in Chapter 25, because this was based basically on my implementation in HCS, which is a little bit different.
I think 1 through 30 are the same. Numbers 1 through 30 should be the same.
Okay. So maybe 1 through 30 is the same, and then I have some preliminary stuff that I'm doing in my program, so I just call those point 1 through point 5. So we'll just go ahead and jump into step 1. And so here what we're trying to do is calculate expected demand. What kind of traffic demand are we going to expect to see on the different segments? And here we have the control for conditions where we might have an overcapacity condition. And so we've got a bottleneck, and we're only going to be able to see on a downstream segment the constrained flow coming from the bottleneck upstream. Background density, you want to say a little bit about background density?
Well, I mean, the background density is basically the density that's expected in the segment based on the inputs.
Yeah, and this is calculated just per the methods in chapters 11, 12, and 13, individual segment chapters.
What's the meaning of background? What do you call the background that's this is the base density?
Maggie, what do you call this background density?
background density is essentially, if you're going to have a segment that will queue, it may have multiple density. The density upstream of the queue, which is basically based on what's coming into the segments before it reaches the bottleneck, and then the density within the queue. So the background density is the one before any queuing may occur. So it is the one that is computed from the individual chapters.
The arriving flow rate?
Yes, the arriving flow rate, yes. But then when there is a queue, the queue may or may not fill the segment, so you have a density in the queue and a density outside the queue, and the density outside queue is what we call background density.
So is it then the overall density based on the arrival demand?
It's arrival flow. It's arrival flow.
So it could be, if it happens after a queue clear, then, the flow rate might actually be higher than the demand. And so that, so the total segment density reported in a partially queued system is essentially the weighted average of the background density and the queue density. We don't report anything in smaller slices in terms of space, but you could have 3 different densities within a segment.
Scott, can you go back to that slide you were just on? The demand is obviously influenced by the bottleneck, and you have to determine if you have a bottleneck based on a comparison of the demand and the capacity, obviously. Is there any case in the procedure where the capacity is different, the capacity changes? In other words, when you do this capacity, you do this expected demand calculation, you go through the entire range of segments of the freeway and the different time slice values. And the capacity, I guess, can change by time period, but forgetting that for the
It could change by 15-minute time period.
Right, but I'm more concerned about changing geographically. Is there any case further on in the procedure where we reevaluate the capacity, or is this the only time?
Well, the capacity is checked at every segment and every 15-minute time interval. The terminology gets really important. We have a time interval and then we have a time step. So with each, and that's part of the user input. So it's a combination of the Chapter 11, 12, 13 capacity and any capacity adjustment factors. Within that 15-minute time slice, the methodology currently does not change capacity. It also treats it doesn't treat it as a stochastic variable, maybe if that's what you're asking. The one case where in L08 we have proposed a modification to that is with the 2 capacity implementation, where the bottleneck, while there's a queue, it would actually operate on the queue discharge flow. We have a user input of whether it's 5% reduction or 7% reduction. And so we basically check every 15-minute time step whether there is still a queue, and if it is, the capacity is reduced by alpha, 5%, 7%. And then at some point, once the queue is clear, it can jump back to the segment capacity. Does that
That's exactly what I was getting at. I mean, I can think of other reasons where the capacity might change as a function of whether or not there was a queue or other conditions, but that's probably the obvious one.
So that's the one change that we have proposed through L08.
Okay, and that
we have a beta version of the computational engine that.
So it's not implemented yet. That probably makes it more complicated.
It's not in Chapter 10. It's implemented. It's described. The logic is described in Chapter 36, 37, and it's implemented in a free valve version that is that came out of L08, but it's not formally the one that's on volume 4. It's not. It requires a subcommittee vote and committee vote to change.
And just to add to, I guess, to Lauren's question, there is also the ability to use capacity adjustment factor to calibrate for a particular site. So if you know that your capacity is going to be different than the HCM, then you have the ability to change the baseline capacity to match a particular site. If you knew there was some issues with using the default capacity.
Would you also want to maybe calibrate the GM density?
That's a parameter that can be calibrated.
That's one thing. I'm a free queue user from the West Coast, so I'm a Dolphin Bay student, and so that was one of the options he provides in his tools to calibrate the density. And when you want to do that in the jam density. One of the reasons you want to do that is because you're seeing queues longer in the field. You got the flows all right, you got that all covered, right? But the queue isn't extending back as far as you see in the field, so then you go with a
Change in
tweak the jam density.
That's a parameter that actually at the very beginning you can reset.
And you can change that in every iteration. And basically, what will happen, so the jam density here listed at 180 to 190. But essentially what you could do is you could override it and, for example, put it at 160. And then what the methodology will do, it will change that speed flow relationship, still linear, but now in a in a different slope basically. And essentially what happens for any given input, you essentially could go from at the fixed bottleneck capacity, you're going from this point to that point, and as a result you have a lower density. And same traffic, lower density means longer queue. It will move, well, I guess it will move at the same speed. Well, no, it will move at a different speed, because the speed in the queue is whatever the slope from the origin to that point. So by changing this, you end up with a slightly faster queue, but you also result in a longer queue. And so you have those trade-offs. Since we don't let you change the shape of this curve, we only let you change this intercept. Well, we let you change that point too, but you will always have trade-offs. But if your ultimate goal is to show correct length of queue, then lowering your jam density will achieve that. Same with Romeo.
Yeah, very important point about the jam density. Those of you that maybe are ever interested in comparing simulation to the results of the Freeway Facilities Procedure, it's something you definitely need to pay attention to. Corson, for example, by default, would give you jam density about 225 passenger cars per hour per lane, or excuse me, passenger cars per lane. Versus the default that you've got like 190 Freeway Facilities. So that'll translate, yes, to a big difference in your queue lengths. Okay, next step is initializing the freeway facility. The point here to stress is just number of vehicles. So a lot of the calculations revolve around looking at the number of vehicles that are on a particular length. Okay, so with that, we're just using our background density and the length of the segment to then figure out what our number of vehicles are, because ultimately we're going to be keeping track of how many vehicles are coming in, how many are going out, and then we can get unserved vehicles from that and so on. That will then translate to future time periods and so forth. Anything else you want to add?
Well, only that actually is what drives the performance measure of density. So at the very end, if we jump ahead to the very end of the methodology, to get your density within any given segment in oversaturated, it's calculated based on these number of vehicles. So you get number of vehicles, you get a flow rate, you have a segment length that is converted to a density, and then that is then converted to a speed. So all your performance measures in the oversaturated are driven by the number of vehicles in the segment and what density that translates to.
And I don't recall exactly what I said before, but just to be clear, for Corson, default was vehicles per mile. Again, Corson doesn't deal with passenger cars. In freeway facilities, we're dealing with passenger cars and the units there. Okay, this is just some administrative stuff here. Again, as Bastian mentioned, basically we're going for each time step and then each segment within each time step. And step 5 is looking to see whether we have an off-ramp at that particular segment. And if we do, we're going to go to step 6. If we don't, we're going to go ahead and jump to step 9. So this section here that you see deals with off-ramp flow. So this might be a good time now, Bastian, to go ahead and modify our diagram and show an off-ramp. And so the concern here is if you have a bottleneck upstream of the off-ramp. So you're going to be metering flow to the downstream segments and potentially, again, to the off-ramp.
So essentially, we're introducing a bottleneck of some sort. that. And we have off-ramp something like that.
Yeah.
And this is, I don't know if you can see that with the lights. There's plenty of rooms plenty of room in the front.
So here you've got a potential bottleneck situation depending on the demand. And so it could be that all of your off-ramp demand that you've specified for a certain time period is not going to be able to reach that off-ramp in the designated time period due to this bottleneck situation. So that's what the deficit calculation is dealing with here. So we need to keep track of off-ramp bound vehicles in a particular time period that can't reach the off-ramp in that time period, and then monitor them for the subsequent time periods to see when we can get them to that off-ramp.
The user input that you specify is essentially a mainline input, traffic that goes overall into your facility, and then you specify the demand at every on-ramp and every off-ramp. And so really the only two numbers in terms of volume or demand inputs are these two. And the reality of this flow here, whatever that demand is, if this volume coming in exceeds the capacity of this segment here, this lane drops, then you end up with a flow deficit at this off-ramp. So the measured volume at this, or the calculated volume served at this off-ramp is going to be limited by the upstream bottleneck. And it assumes basically proportionality. We don't have ODs. We don't have ODs in freeway facilities. If you're keeping track of limitations, that's a pretty big one. Right? We're assuming a proportional allocation of that input to these various outputs, and so we reduce that number. Another quick caveat, if you are trying to enter this number from a user perspective and you have congestion, then you actually need to make sure you come up with a demand number somehow. And there's actually a procedure in Chapter 25 to adjust a field measured volume served to a expected demand, because that's what you enter in the method. Joel, do you have a question?
Oh, just that quite often when you go through those bottoms, and once you go past it, traffic actually opens up and moves. So if you impose a bottleneck every so often, you create an opportunity for traffic to move beyond it, right?
Right. Yeah.
It will arrive later, that's all it
Yeah.
does.
The idea is that
But it doesn't show up and you can't really
this is just making up numbers. So this is a demand of 4,000, and here you have a capacity of 3,000, and then you have a theoretical on-ramp, off-ramp demand of 1,000. Then it basically will account for the fact that, okay, well, 1,000 vehicles or 1/4 of the demand is held up somewhere, and it basically will take that and turn it into 750, with the rest of the demand being processed in the next time interval.
Yeah, I think, like Nagy was alluding to, this again, an important point is that, if you're looking at the output from freeway facilities, you may see a particular time period that the amount of flow served is greater than the demand for that particular time period, because you've got carryover. So that might be a situation where you had bottleneck, and so you were limiting the throughput in that particular time period, and then it got carried over to the next time period. So now you see the actual amount of volume served is greater than what the original input demand was in that time period.
Eric, got a question?
In this situation, if you have a very large off-ramp volume, would you make any attempt to bias the levels of traffic across the lanes? Do you have more traffic in the right lanes, or do you still equal across the lanes?
Okay, I hope somebody's keeping the list of limitations. Yes, it's another big one. Other than the undersaturated on-ramp, off-ramp method, where we have the ramp influence area, for all other segments, we assume a uniform density across all lanes. And for this situation, that is not necessarily the case. It's also not true, another big limitation before anyone asks it, if you have a signal or any other bottleneck here that results in a queue actually spilling onto the main line, we currently have no way to model that. So, and that's probably, I would argue, the biggest limitation in this methodology, because it happens all the time. It happens all the time that you have a diamond or whatever interchange configuration, you have a queue that spills onto your freeway, and we have no way, other than a warning message that says your off-ramp is over capacity. But that doesn't help you much. So you could manually go in here and reduce the capacity here, but we currently do not have a lane by lane or any sort of adjustment of density within this area. Again, with the caveat of the base method in Chapter 13. Yeah.
This can also, what you've drawn can also be very similar to what you see in most freeway systems, is an on-ramp coming on and creating the same type of impact than an off-ramp, right?
Yeah.
And one thing, I try to be more, think about solutions oriented, and one of the approaches I've thought about and talked to people about is changing the on-ramp and off-ramp to an off-ramp and on-ramp with, say, an auxiliary or a CD or something in between. Say you have 6,000 vehicles, 500 getting off, 500 getting on. You end up with 6,000, 5,500, 6,000. So the bottleneck never occurs.
Right.
Versus 6,000, 6,500, 6,000. So it seems like how we design interchanges and on and off ramps, we've been doing it wrong.
Yeah.
If we could just make a slight modification to how we design our freeways and a lot of them that are failing, and we go up, first thing we want to do is go up and add a fourth lane and widen and lengthen the bridges and create a huge amount of infrastructure that we could have probably simply designed the off and on ramps a little bit differently, and it would work.
Sure. Yeah.
At least it would work longer, and they might keep you from adding an extra lane.
Well, and as we're talking about limitation, we do have a new chapter on interchange ramp terminals that has, a lot of sensitivity on different interchange forms, and through work at FHWA, the double crossover diamond now gets added to it, and so forth. But we have no way to integrate any of this knowledge into freeway facilities because it's in volume 3, and so naturally the two shouldn't, mesh. Right?
I agree, they need to work together.
Yeah. So I'm glad we're having a committee-wide workshop. So this is.
Since you brought up the uniformity across all lanes limitation, I'll give you a couple more motivations. This for HOV lane analysis, where you have continuously accessible HOVs, so you have uneven usage of the lanes. And then the other time would come up where it'd be nice to be able to do a lane-by-lane analysis would be for like truck lanes, truck climbing lanes, long steep grades. Especially when an agency is looking at establishing a rule or a policy of limiting trucks to only the 2 right-hand lanes, our methodology would be sensitive to that right now.
Right. Yeah, I'll let Scott proceed, but I'll hang out the line.
Not to mention active traffic management, where you add an extra lane, shoulder lane during peak hours. But I just mentioned this.
We do have, the only place where we do have special, there is a managed lane procedure related to FEMA, the managed lane, even if it's a diamond lane, is handled separately from the general purposes. But that's the only exception.
Okay, yeah, we've got a lot of steps to go through here still, so I'm going to jump to step 9. So again, this block here with step 6, 7, and 8 are dealing with some differences in the deficit calculation, but again, the idea was just to talk about the overall concept of the off-ramp deficit. And step 9, now we're just trying to determine what's our mainline input here. And so we're looking at our mainline flow from an upstream segment and adding any on-ramp flows, subtracting any off-ramp flows, and then also looking at unserved vehicles from the previous time step. Now we're going to get into the section that deals with on-ramps. So step 10, we're just asking, do we have an on-ramp at this node? If yes, we're going to go ahead and go to step 11. And so maybe, Bastian, you want to modify the figure down there to have an on-ramp? Sure.
The on-ramp for the bottleneck?
Yeah, I wouldn't worry about the bottleneck.
Or just the on-ramp?
don't add a lane drop, I guess.
I had a question about the previous example, actually, just terminology. Bastian, what did you call it? What did you call the name of that phenomenon when the demand on the off-ramp can't all get there?
Flow deficit is what we
Flow deficit. Is that analogous to the concept of demand starvation?
I think so. I was thinking the same sort
I
of
mean,
sharing.
should we be using consistent terms? Just a question.
Well, I think ideally throughout the highway capacity manual, it would be nice to have consistency in terms. I think we have a number of locations now where we are using same variables or same terms that mean different things. Mostly across chapters, but apparently there is a situation that's brought up where we have inconsistency within the same chapter. Hopefully, yeah, that's something we can address in the ASIM 2015 update. You want to talk a little bit about just the concept of on-ramp input?
Sure. So we still have our 4,000 here, and then basically we would want to add some sort of a demand to that on-ramp. And so again, those are essentially the only demands that you enter as a user: the mainline in, and then all on-ramp, off-ramp demands. And you never input whatever volume goes through here or whatever demand, because that is all estimated. It becomes a function of the mainline in and the ramp in, and then it changes throughout the methodology, throughout the analysis, through queuing and so forth. So all you really need to worry about is those. Maybe one thing to mention is that you can vary truck and RV percentages for any of these, and then the method will also calculate the weighted average. Again, there's no OD. Thanks for reminding me that we have no way of modeling, for example, that if this is 5% trucks and this is 20% trucks, we're just assuming that then whatever the mixture is here, that they get uniformly distributed downstream. We have no way of, other than calling something. Of course, we can have an off-ramp also saying 20% trucks, but we can't really say, well, these guys go there and these guys go here. I mean, we just don't have that detail. And it's a limitation. I don't know that we'll overcome it. It's a simulation application.
So with the on-ramp input, we're looking at potentially what the capacity is of the on-ramp. And if your demand is exceeding that capacity, then you're going to have queuing, and that queuing will carry over in subsequent time periods and add to your on-ramp input. While ramp metering is not explicitly modeled within this methodology, if you have, for example, a fixed ramp metering rate, you can use that as your demand input from that on-ramp.
I have the next limitation. Before anyone else asks that question, when you're using the methodology and you're using FreeVal, and you ever look at your ramp queues, we report the ramp queues, and they're very, very long. You will easily get 10-mile ramp queues that come out of FreeVal. And typically, they're used in the system delay. They're not used in the mainline delay, so they're easily ignored. And if they're large numbers and you can't explain them, then ignoring them is always a good practice. But one of the big limitations is that we have no way to actually model what the ramp densities are. We're modeling the on-ramp queue at the same density of the mainline, and I would argue that they have very little in common. So that if you're in a situation here where you're mildly congested, and you have densities of 60 or something like that, we're essentially propagating that density of 60 passenger cars per mile onto the on-ramp, and we have no bunching algorithm of any sort. And arguably, every time I'm stuck on an on-ramp, I'm bumper to bumper. I'm at jam density. The methodology, however, assumes that we're propagating everything at the mainline density.
There's no requirement for that. You're just doing the methodology is just doing it out of convenience, right? There's nothing in the methodology requires you to assume that the on-ramp density is the same as
No. But we have no guidance or data currently on what it should be. So, of course, we could make another assumption, but we can't change the status quo without empirical support, right? Sure. Is that the idea? Yeah. I guess. I don't know if we can.
Doesn't stop us before.
Yeah.
You can make it a user adjustable variable with that.
With that, yeah, sure.
So that's the difference between metered or not metered ramp, because a metered ramp, the vehicles are stopped. So you use a stop density, they aren't moving.
Right. Yeah.
Well, if it's not metered, then yeah, then the question is, how fast are they moving?
Yeah. I'm pretty sure that we have a separate variable for the on-ramp density, although I'm not sure now. And if not, it would be a variable to add. But again, it's there's lots of work to do. So go ahead.
Okay. Again, I don't want to get into all the details here. I think just generally, again, we want to talk about the concept of you've got an on-ramp segment, and you might have a situation again where the combination now of your mainline flow and your on-ramp flow is going to exceed the downstream capacity. So now we have to figure out how to deal with that, and that's going to affect the amount of on-ramp traffic we're going to allow into the segment, and that's going to relate to the MO1 constraint we're going to get to in a minute. Again, you want to qualitatively discuss what's going on here?
Yeah, I mean, it's code language of whatever is written on the left side of the board, or at least some of them. So RM is ramp metering. ONRC is on-ramp capacity. SC is segment capacity. Then the minimum of mainline flow plus on-ramp flow, this is the MO3 constraint, which is the front clearing queue constraint. And you also need to be really careful here where you have segments I versus I plus 1, and time interval T versus T minus 1 being the previous one. So we don't have this diagram, but essentially, if you think of a matrix of cells, it basically looks at what's left over from the previous time interval, what's happening in the next downstream segment. And so a lot of these variables they're all defined in the code, in the computational engine. They're used consistently in the chapter, so they're the same variables. And in fact, even these steps, step 12, if you open FreeVal and go to module 6, search for step 12, you'll see exactly those equations. They won't be written like this, they'll be written out in Excel code basically. But it's possible to get behind all this and to troubleshoot it. It's just a lot of numbers, and it takes a little bit of time to really think about where I and I plus 1 and T minus 1, where they are located in this, in the cell transmission.
We got into a little bit of discussion in the webinar about, so how do we deal with that situation where a combination of your mainline flow and your ramp flow exceed the capacity? Bastian brought up the, what was it, Sharp 2 CO5 report. So I think FreeVal has some additional logic in it right now. What's in HCS is basically limited to what you see in the middle line there, lower block of those equations, which I believe is all we have documented right now in chapter 25, which basically says when you get to that overcapacity situation, we're going to go to an alternating, kind of every other vehicle type of ramp merge situation. So we'll allocate half of the capacity for that outside lane to the mainline flow and half that capacity to the on-ramp flow. But this is another area where we need some additional documentation. Meg, you want to jump in?
Just want to kind of read this to the count times back.
Yeah, free queue uses.
So this is an area where we need some additional documentation as well as some additional discussion about, is this really the best way to do this? If we want to add some additional logic to that, such as what's in the CO5 report.
So, I don't know, I'll probably get turned around here, but ultimately what we're talking about is that we have segments I, we have a subject segment, we have a segment before, and we have a segment after it, and then we have to find the node, I think this is correct, that node I is the one upstream of segment I. And then we have our analysis time period, we have T minus 1 being the previous one, T plus 1 being the next one. And essentially we are asking for, what is the flow coming, what is the demand coming in here? We're looking at, for example, unserved vehicles we'll get to that later, unserved vehicles from the previous time step. We're looking at what happens in terms of queuing on that actual segment, so the segment capacity, IT, the mainline flow of the next downstream segment. So there's kind of a logic to all this, but I think we probably don't do a really good job in the chapter explaining where all these different kind of terms fall in. And so we use a cell transmission approach, but we never show this kind of a matrix. Where each of these would be, see, I got tripped up myself. They're not time periods, they're time steps.
Yeah, the time periods would be the 15-minute block of time, and then the time steps are, as we have it by default, the 60 time steps within each time period. So 15 seconds per time step in the default situation. Now here we're looking at maximum output from the on-ramp. And so now the question is our on-ramp output greater than or less than our on-ramp input? Let me jump ahead here a little bit. Okay, so I want to get to the section here that talks about the mainline output. So this is the constraint condition again that's dealing with essentially the bottleneck created where the combination of the mainline input and the on-ramp input is going to exceed your downstream capacity. Anything else you want to expand on?
Well, yeah, and just to basically, all these different flow constraints, they kind of interact. So you have the MO1 constraint, which we call the on-ramp constraint, is itself constrained by the segment capacity of the segment minus whatever we are processing through the on-ramp, or the MO2 constraint, which is essentially if that segment was already full in the previous time step and we can't get traffic in there, or the MO3 constraint is if there's a front clearing queue in that segment that hasn't reached that segment yet. And so we just basically have to check that every time. So we can't, the MO1, we can't process more traffic across this red node than the minimum of those three. The capacity minus the flow, the previously queued vehicle, or any front clearing queue impacts.
Quick question. So if you reach capacity in oversaturated conditions within the 15-minute period, does your capacity drop within that interval, or do you wait until the next analysis interval to drop the capacity?
So currently, currently it doesn't drop at all. Like with the queue discharge currently doesn't.
So for the LOA?
For LOA, we basically say once there is a queue that reaches a segment, then we reduce the capacity by whatever that percentage is. And that happens instantaneously. So that happens as soon as, so the actual bottleneck, it happens at the beginning of the time interval, because that's when the demand will exceed the capacity. But really, we're doing that check for any segment, basically asking whether there's a queue on the segment, and then we reduce the capacity of the segment. That's the actual check. So it's DURC greater than 1 with the active bottleneck, and we keep that capacity drop until whatever queue is in the segment has cleared. We'll implement that for any of the upstream segments as well, but we'll never end up using it. Because the flow of any upstream segments, they're always going to be constrained by MO2, what happens downstream. And so as a result, the actual segment capacity is never the prevailing constraint. If you're a segment upstream in a queue somewhere, typically the limit of what happens in terms of downstream storage is always going to be less than the theoretical capacity of that segment. But it happens in the next 15-second time step, essentially.
Okay, so it happens within those 15 seconds.
It happens for the next 15 seconds. Yeah.
Okay.
Yeah.
And so does that create an impact upstream in the flows? that you took track of?
Well, essentially, the computation is repeated for every cell. And in a way, the computation actually, it kind of goes backwards.
Okay.
So the way the steps through is essentially it goes this way through the facility, and then it goes back to the end, and then it propagates cues this way. So that's essentially how it steps through. So it's kind of presented sequentially, but really the calculations happen backwards.
There's a question.
Doug, you had a question?
Is the capacity drop put in by the user, or is it part of the program?
In the L08 implementation, there is the opening dialog allows the user to pick a value between 0% and 10%. The default is 5. We've actually done some literature search, kind of a literature synthesis, where we found an average of 7.1% across 14 studies or so that have been done nationwide, including Canada. So, but we allow the user to change it from 0 to 10.
Step 17. Here we're checking for a queue situation, so if we have demand for capacity, we're in a queue situation. We need to check to see if we have a front clearing queue. So again, Bastian talked about a couple different queuing situations. The MO2 is dealing more specifically with your kind of classic bottleneck situation, where you have, for example, a lane drop, something like that, and your demand is going to exceed that capacity there. The MO3 situation might come about, as Bastian mentioned, say, for example, in an incident scenario. So you normally have a certain amount of capacity, and you have an incident situation that reduces the capacity, then the incident gets resolved, and the capacity increases again. So that's going to be a little different situation there with how the queue is going to clear. That's kind of analogous to a traffic signal situation. Cars are stopped, they're queuing up, the light turns green, and so you have a front clear queue situation. And so in that case, that's where the shockwave speed comes into play, because the queue is clearing from the front, but the back of the queue, basically staying stationary until the queue clears out in front, or additional vehicles as they arrive are going to get added to the back of the queue. So we can't start moving vehicles into that downstream segment until that back of queue situation now is resolved, and that's again a function of the shockwave speed. I may be getting a little bit ahead of myself here. We've got a slide. Okay, pretty close here. So, and again, I think Bastian's kind of illustrated this here with the flow density graph that we have up here. I'll let you just expand on that.
I think, well, in reality, it's in there in principle. In reality, it's very, very difficult to show this. And in fact, we've been, training courses, we've been trying to come up with some example problems to really show this incident effect and so forth. And it's, if you look at the raw calculation, the time step by time step, you see it. But in the 15-minute output, it's going to be very difficult to show these. But it's, it's in there in theory, and it's an important component. It's an important one for, again, a reliability analysis where we do work with incidents routinely. But, it's probably not very high on the list of priorities for kind of the standard Chapter 10 analysis, which is more of a bottleneck-driven analysis, or even, for ATM, but it's in there. So.
And your shockwave speed just ends up being the slope of this particular line here, because one of your endpoints is going to be your density and capacity of 45 passenger cars per mile per lane. So it turns out that again, with our default jam density of 190 passenger cars per mile per lane, 190 here. So it's going to work out to be something like 16.5 miles per hour shockwave speed.
And I think this is an exhibit directly out of the HCM, and I think that's where some of the confusion comes from. That we'll talk about Chapter 10, and I looked at Chapter 25, and I see you're doing shockwaves. It's like, well, no. The problem is we've generated this graph for the front clear queues, but we never generated a graph like this to talk about the cell transmission approach. And so really, the shockwave implementation is a very small component. It's really only in the case of front clearing queues when it ever prevails. But people don't like text; they flip through pages, right? And they see a diagram, and so now all of a sudden we're doing shockwave. So this is probably our number one learning outcome for the day is kind of understanding the two different components. The diagram is still important because the slope here, or the shape of the oversaturated flow density, does determine, in this case, these blue lines, the density in the queue. So we're getting those numbers from the same graph, but we're not then translating them into shockwave speeds. We're simulating it using a cell transmission approach.
Okay, step 20 is calculating the density.
Perfect segue right there. Perfect segue. That's the equation. So it's the density in the queue is the jam density minus jam density and density of capacity times the segment flow and so forth.
It's the KJ, jam density.
It's a triangle.
Density, capacity, the KC.
Yeah. It estimates the density in the queue as a function of that triangle. So that equation 25-7, if we ever get to our, well, I'll put the limitation up there in a second, the shape of the oversaturated curve. So if we're ever making any changes, this equation is going to be more complicated. So if we're ever taking this whatever this red line is, and if we ever use some of the research that comes out of Sweden and Denmark that we saw at the International Symposium, where there were some relationships that look more like this. If we ever want to do that, then to get from jam density to this point, we basically have to replace that with whatever this equation is. Right? So this is starting to see, and if you have access to the code and understand the variables, you could actually test the impact of your own oversaturated speed flow models and get some differences. Thank you.
Just a couple of comments here. One is you typically will not see that number unless the segment is fully queued. As we mentioned earlier, if you have a segment that is partially queued, what you will see is the combination of the queue density and the background density that it was asked about early on. And then the other question, and I can't remember, are we reporting at the end of 15, what are we reporting?
Yes,
at the end of 15 minutes.
At the end of 15 minutes, we are reporting the average density over 15 minutes. And if you look at that number and you do your theoretical, what's my Q density, it's 100, and you look at the free valve output and it'll give you 82. And the reason it's 82, not 100, is because it's, the density in the segment slowly but surely grew. At the end, it was fully queued, it reached 100, but on average over 15 minutes, it ended up being 82. In the next time interval, it will likely jump to 100, but if you look at the densities within that segment, within a queued segment, the first time interval, when there is queuing, the reported density will be lower than the queue density because it reports an average over 15 minutes.
But the queue itself is at the end.
The queue length is at the end.
At the end.
Yes, and that's the confusion. Those two numbers are not the same. They're all in the code somewhere. If you trace those variables, you will see them, but the two numbers are not the same.
The queue length is for the end of the 15-minute period.
The average of the 15
The
minutes.
average density.
Density is
across the whole 15 minutes.
Yes, yeah. The length is at the end, the density is the average. Currently, I don't know, that's really just the reporting that comes out of the software. It can be changed, obviously. Lauren.
Okay, so I had one question, now I have another.
Okay.
Or an observation. So in the case of when we have queues either growing or dissipating,
Okay.
particularly for long segments, the calculations are pretty complicated because you're basically dividing that segment into two parts and the delineation between those two parts is dynamically changing every 30 seconds or however often we're doing the calculation, right?
Yeah.
So I guess that's sort of your problem, but it's really our problem because I'm guessing that code is probably one of the most complicated parts of the procedure, right?
This whole code is pretty complicated. Yeah.
But if you're going to something like a a nonlinear curve like you were talking about from the other research, that would complicate it further, right?
Well,
It's not really a question, it's an observation, I
not
guess.
really, because ultimately, I mean, it's the density is recomputed, yeah. Here's what will make it complicated. Changing the curve from the solid to the dashed is easy, but having the density within the queue change over time, that's what gets really tricky. And that, you know, the list of limitations is going to go down the board. Right now, if you have a fixed demand, fixed capacity over 3 hours, the density of the queue will be fixed. It will be fixed at whatever that drop-down blue line is. We don't have any queue bunching algorithm. And I'm actually not aware of any data that has looked at freeway queues over time, sustained freeway queues, and whether they stay at, you know, a density of 100 or whether they begin bunching to get closer to jam density. But right now, we are only changing the density as a function of whatever the bottleneck capacity is. We're not changing the density dynamically over time.
Okay, my second question about the queue length. I think we're okay there, but I think it was Rick's question. You said the queue is the average of the time period.
Yes.
Right.
No, the
Queue
density.
Queue length is the length at the end of the...
At the end, okay. And because our demands, I'm just thinking aloud here, because our demands are in 15-minute time periods, that's going to capture over the course of a bunch of 15-minute time periods. It will capture the longest queue. Because by definition, the longest queue has to be at the end of one time period, which is the beginning of another. So we're safe there.
Yeah, we'll capture the longest queue. Yeah.
Okay, there's a little bit of discrepancy because the density is an average density, but I don't know. From an application standpoint,
the
that's
biggest
not relevant.
challenge is really, you know, if you get an audience that actually, you know, kind of follows and you're trying to present the data and, you know, somebody asks the question of, I don't understand these densities. Why are these densities changing? You know, why are they going, well, undersaturated, I understand they change, but then in oversaturated, why do they change? And that is one reason.
And again, the reason we have to do it is to match the fundamental relationship that flow equals speed times density. We're giving you space mean speed over 15 minutes. We're going to give you average density and average flow over this 15. It cannot be a single observation. It's going to be the average.
You can also get average too, modern estimation. You can also get an average if you want and over that interval.
You could get an average Q, yes.
Again, with just the time, I think we can...
I think this is actually a key one. I know we only have 20 minutes, but this is the MO2 is the constraint that probably prevails most frequently, right? Where the MO2, which is the traffic, you know, it's all still the traffic that can get processed through a node. It's a function of the mainline flow plus any off-ramp flow minus any on-ramp flow, and then plus the potential storage downstream. KQ times Li is Q density times segment length. And this should actually be times, I guess it must be number of lanes. KQ must be already scaled by the number of lanes. But it's basically the allowable storage minus the number of vehicles that are already in the downstream segment. And this is where the T-1 comes in. So in order to look at how much flow I can have in there, I need to look at the previous segment to see how many vehicles were already on it. And if the segment is fully queued, then essentially whatever that output constraint is, essentially is limited by, you know, by how much leaves the segment at the next node down. The MF I+1 is the flow leaving the segment in the previous time interval. I can see it. This is where I tripped up. The first term is how much traffic is leaving that time or left that time interval, left that segment in the previous time interval. How many vehicles are in there, and then what are these various other flow constraints? So that's the one that in an oversaturated situation, probably 9 times out of 10, this equation is the one that will limit the flow across a node which then in the next step translates into the flow in the same. So that's the equation 25-8 is probably the one that prevails most often.
Yeah, so again, you've got those three major constraints, MO1, MO2, MO3. So I think it's important for everybody to have a good feel for those. So what I was going to say is really the rest of this is kind of a lot of administrative stuff. Again, keeping track of, updating your various variables, mainline flow, segment flow, and so on. So we can probably kind of breeze through these last, again, Bastian, if there's anything.
Oh, just that's the list on that board. Right. So mainline flow constraints. If I go down the list, the upstream capacity is I-1, the downstream capacity is I, MO1, MO2, MO3, and then the mainline input. Those are all the flow constraints. So it's what's on the board is a text version of equation 25-30.
Yeah, so these are all going to get checked for each time step, and then whichever one's lowest is going to be your controlling variable. So if you just, I don't know if there's anything you want to say as I'm kind of going through this. Like I said, again, it's just doing a lot of variable updating at this point, updating the number of vehicles on the segment, figuring out how many unserved vehicles we might have that are going to carry forward to future time periods and so forth. And again, just the administration of the iterative approach, going to the next time step, next segment, and so on. And then we get into calculating the performance measures for each of the segments and the facility for each of the time periods. That's about it.
You mind pulling up your big flow chart?
Sure.
Because that is, if you're kind of used to looking at code, or at flow charts, you'll end up seeing three big loops. And that's really, so all these steps that we have just gone through, there are three kind of nested loops. And that's ultimately what the procedure is going to end up doing. And so the first loop goes from step 4 all the way up to step 27. And that is basically going within a 15-second time step, it goes through all the segments. Okay, so it's the entire facility going through all segments, however many they are. Once you're at the end of the facility, you basically go into a loop from step 3 to step 29, which is stepping through all 15-second time steps. Within each time step, you're still going through the loop of 4 through 27, but you're basically repeating that every 15 seconds until you get to the end of 15 minutes. And then your biggest loop is from 1 to 31, where you repeat that for every time interval, every 15-minute time interval, until you reach the end of queuing. Not the end of the analysis. You do this until all queues have cleared and you no longer have D over C greater than 1. And so really the step-by-step procedure, really the heart of the method, the cell transmission model is step 4 through 27, which goes in every time step all the way through the facility. And then 3 through 29 repeat step for all time steps within 15 minutes. And then 1 through 31 repeats it all for your overall analysis. And that's why it's implemented in software, right? That's why you don't want to do these things by hand. That's the basic flow, and if you're trying to understand the method, really 4 through 27 is the key one to understand. Everything else is just redoing it a bunch of times.
What's the sense of the subcommittee regarding the level of documentation required yet?
I don't know, Mike, if you want to answer that, or I can start, and then others feel free to weigh in. I think the biggest concern that I would have in terms of documentation, well, there's two concerns. There's one is the general understanding. I mean, I don't know how understandable the last hour and a half was, but believe me, reading the chapter is worse. So, and so it's just, and having this flow chart split up over 6 different pages, I like to see the big picture. And when I read chapter 25, I don't see the big picture. And so I think there's an explanatory need. There are, however, a whole series of sub-steps that are not documented. So, For example, the on-ramp queue allocation that's in Sharp 2 CO5 final report, it goes over 10 or 11 pages of documenting that method. It's not in here, and it should be in here. And there's some other cases too where it's really not well documented.
Well, and honestly, also in the process of starting Freeway, there was a lot of holes in the ATM procedures that we had to fill, and probably were shortcuts that we had to make the procedure work. So some of these ended up being documented, some were not.
What's in Chapter 25 is part of the 2010 update. There's actually a whole series of flowcharts and tables in Chapter 25 that I think Jim Bonison had put that concept together of linkage lists and flowcharts for the different modules. And so those directly tie back to the computational engine. So all of the variables we've talked about today you'll see in the code. All the modules, when you open FreeVal, are actually listed in Chapter 25. And there's an explanation of what they do. And every variable used in every module is also shown in a table. It basically says, okay, module 6, step 1 does this. So there is a lot there, but it still looks like computer stuff. So it still requires a certain level of comfort, I guess.
Okay. Any other questions before? Dave?
Maybe just one suggestion for the computational engine or engines, segment-specific calibration, because some simulation users feel that segment-specific calibration is sometimes more important than the global calibration. Maybe just something like jam density on a segment-specific basis could be helpful for some people.
You can calibrate capacities. So the other thing you can do with this is, so you can't change jam density. You can't change this, however. So you could go down.
Well, you would change jam density for the whole facility, right? That gets applied across all the segments in the facility. You can't change it at the segment level.
But this capacity adjustment factor of 0.95 or 0.9 or whatever it is, you can change that at any segment at any time interval. And so that, of course, changes, well, it does a few things. It changes on your undersaturated. It actually uses its equation 25-1, where it fits a new speed flow curve here, but it also fits a new speed flow curve here. So that line is then calculated. And so essentially you are calibrating both undersaturated and oversaturated by dropping that capacity. However, you can't, you can't change jam density, but those are the two you have. What we've proposed through LO8 is that we actually also let you change the free flow speed. So this is going to be really impossible to draw here, but if this slope is the free flow speed, we have proposed through LO8 that you should also be able to actually calibrate the slope of that line for weather, for example. Right? Your free flow speed under a heavy rain event is not going to be 70 miles an hour. And so that's a proposal where you can change the speed adjustment factor, and that essentially would also change the shape on the undersaturated side. It won't affect the oversaturated.
But users can do that now. Not with a speed adjustment factor, but they can put in their own free flow speed.
You can put in the free flow speed. Yeah.
Okay. So if I'm doing a big Carter study with the Freeway Facilities chapter, and I need to calibrate to existing conditions,
Yeah.
changing the capacity and free flow speed is a pretty powerful means of doing that. Now, someone reviewing my work might say, well, you're just entering those numbers so you get the answer you want.
Right.
And I guess depending on how I do that, it might be okay or it might not be. But I think that's, because this is so much like a simulation model, and it's very similar to FreeQ that Rick mentioned.
Yeah.
I mean, that's what users of FreeQ
Right.
did.
Well, and I don't know if this is the HCM's job to offer calibration guidance, but I think it's certainly there's a demand there, on the freeway side for sure. The other big question, really going back to your documentation when we do workshops on this, on the freeway facilities method, the biggest stumbling block is the segmentation. That's taking a facility and dividing it into these different segments. I mean, it looks really easy here, but a real-world facility looks nothing like this. And it's the biggest stumbling block, and we've been getting some free valve models for the L38 contractor teams, the teams that were selected to test the LO8 method. And I just looked at one last night where the segments, I haven't even seen the main facility, and I just know that the segmentation is off. Because they're not, they're overlapping ramp segments everywhere. And it's just, I think that's a big knowledge gap, probably, in terms of misapplication of the method, actually understanding where to draw the lines. When you don't have a clean 1,500-foot ramp influence area, because in reality, it doesn't look like this. In reality, it looks like this, and then you have a ramp here, and then, you have an upgrade halfway in between. And then, how to separate that is not always clear.
Is it an issue of lacking guidance or difficulty in applying the guidance that's there already? Because I think that the issues in the HCM don't necessarily do a very good job of explaining the segmentation at that level.
And it might be more of an HCM, AG, applications guide challenge, where how do you take chapter 10 and how do you apply it where segments aren't clean? How do you go about taking, and we have a whole series of these examples, where, well, is this a two-sided weave or is it an on-ramp, off-ramp, and there's kind of a lane add, but I know from local knowledge that there's a lot of weaving friction, and so it takes also some judgment to ultimately pick the segment that will give you the performance that you want, and that's not always straightforward. So.
A few minutes left. Questions from the floor?
Actually, maybe it's good to talk a little bit about what happened in LOA, since we have a full committee in terms of the major additions that were done in LOA.
Right. So the major additions, and I don't have a list here, but let me try and draw as opposed to put a bunch of PhDs in a room with a whiteboard. You don't know what's in the
Rick, you want to turn on the lights in the front?
Turn on?
The lights in the front, turn on the projector. Thank you.
The biggest thing in terms of LOA is currently we have we look at chapter 11. We have in our speed flow diagram, we have a free flow speed that goes up to some break point. Then we have this curved portion up to whatever we call our capacity. That's defined at the density of 45. And then really, what happens on the oversaturated, that emerges out of chapter 25. We've always had this capacity adjustment factor here that essentially drops the capacity along the 45 density line, and then there's an equation which is now 25-1 that connects the two. That equation, by the way, is not based on field data. It's based on expert judgment, Maggie, right? Is that what you call it? But this equation is in there. Well, we've said with LO8 as well, wait a minute, this is really not enough, because we have cases where we may need a speed adjustment factor. And Lauren, you mentioned you can already change the free flow speed, but then the question is that the problem with changing the free flow speed, it changes your delay baseline. Right? If you change your free flow speed, all your delays are now estimated relative to the new free flow speed. And in LO8, delay induced from a weather event, we want to reference back to the black line as opposed to whatever this lower is. So we have proposed a modification of 25-1 that essentially lets us fit the speed flow curve that looks something like that. With some limits, that if your speed drop is more than your capacity drop, then you don't get an upward curve, those kind of things.
Yeah, those are two different things, though, Bastian. I think the speed adjustment factor is due to an external condition of the weather.
Right.
Changing the free flow speed in a calibration setting, assuming it's done in a correct manner, should change the delay either up or down, depending on where you're doing it.
That's correct.
So that's okay by mine.
Yeah. Well, but so it's important to know that currently, if you're changing this number, all your delays are going to be relative. So this was a big change in element.
I think just to finish the calibration thought, I think that's important though, is that it shouldn't be doing calibration with the speed adjustment factor, because that will
that will change your baseline.
Change the delay in the
Correct.
wrong way. So
Correct.
maybe that guidance is needed at some
Yeah,
point.
correct.
So you're adjusting the speeds and the capacity rather than free flow speed with the verification population?
Yeah, we're basically changing this point and we're changing that point. And then we have an equation that fits a curve in between.
Okay, are you adjusting the, are you using a different curve then?
Yeah, we basically, that equation 25-1, we basically added some terms to it. The second big change in LO8 is the Q discharge, where basically, whatever this throughput is here, that's similar to this capacity adjustment factor, that you could have a Q discharge drop alpha of whatever, 5 to 7%, that then reduces the throughput while a queue, or the throughput to a bottleneck while a queue is out. And so that was, that's based on a lot of research that basically shows that effect, and so that's one thing. Another very, very big change in LOA is that right now, in the HCM 2010, you have no way of calibrating a weaving segment or a ramp segment. So the capacity adjustment factor and the speed adjustment factor assume a basic segment. And you have no way in Chapter 12 and 13 to change either of those values. And in fact, both Chapter 12 and 13 are not always true to the fundamental relationship, to where you do a capacity check first, and then you estimate speed, and so forth. So changing the capacity in Chapter 13 in the weaving segment will have no influence on your speed results, because the two are independent. They're independent regression equations. So the big challenge in LO8 was then, well, how do we go about modeling weather effects in a weaving segment? How do we do that? Because right now, what happens in the current free valve, if you put a capacity adjustment factor, it overrides whatever segment it is, and it uses that dash column. So in a way, it ignores the weaving method, and it treats it as a basic segment. The problem is, you could have cases where your Chapter 13 weaving speed, let's say, is here, and then you do a capacity adjustment factor due to weather, your speeds go up. And so because of that inconsistency, we basically went into Chapter 12 and 13, into the algorithms that Roger had developed, and basically implemented or proposed an implementation for CAF and SAF within Chapters 12 and 13. Not based on any data, just based on looking at the equations. And wherever it said C, we now put C times CAF, and wherever it says S, we put S times SAF. But that's a change we had to do to avoid speeds jumping up when it starts raining. I think those were the big ones. I don't know if we had some new performance measures. Obviously, we introduced travel time index. That's what everything is based on. We also put a denied entry queue length calculation, because a lot of our scenarios had queues that did spill back beyond the beginning of the facility. So we just calculated that queue length and report it now. But I think in terms of the three really algorithmic changes, it's the two capacity, it's the speed adjustment factor, and it's the CAF and SAF for weaving implements. And there's a TRR paper from last year that also documents all those. That was accepted by the committee. Speaking of, so Hale is here.
I just thought of another question. This has nothing to do with LO8, but on the weaving methodology, Roger may have to help with this. The determination of whether it's a weaving section is based on the geometry and the volume. I should say, probably demand. So for an isolated weaving section, that's relatively straightforward. But in a case where the queuing is affecting the demand and the volume, are there cases where you come in or out of a weaving section definition during the evaluation within free valve?
Well, he's got mine.
That's saying no.
Yes. Well, so, but independent of queues, the weaving, whether or not a segment operates as a weave, it depends on the lane change rate per mile, basically. And so, because we can't change the segment length, but we can change the demands and the ramp patterns from one interval to the next.
Yeah,
And so
it can
you-
change by time interval.
By time
Every 15 minutes.
Right.
It does that now in
Right.
the HCS version,
Right,
but
sure.
not within the individual
Well,
time period.
here's what I was thinking.
Not to the queuing, but
Yeah, well,
from one
well,
time interval to the next.
Let's say we have by the calculations of HCM calculations, we do have a weeding section because we have a high rate of lane changing
Yeah.
based on the demands. But let's say we have a downstream bottleneck that is limiting the flow through that section. You're going to have a lot less lane changing. It may, in fact, not be a weaving
Once,
section.
once the queue reaches that segment, the weaving method is thrown out.
Oh, it turns out entirely.
So,
Okay.
so once the queue reaches any segment, chapter 11, 12, and 13 are ignored. But yeah, but it could happen, and so this is important, if you have a weaving segment and you have 15, 30 minutes of high turbulence and then everything is fine again, you could have over a 4-hour analysis period that a weaving segment is only analyzed as a weave for 2 or 3 time periods, and then it's analyzed as a basic segment. And in FreeVal, you'll see that as W-B, meaning user entry weave method analyzed as basic. The same is true for continuous lane adds and lane drops. It's another documentation challenge. In the HCM 2000, there was a paragraph that said if you have a freeway and you have an on-ramp with a continuous lane add, that operates as a basic segment. FreeVal still used that assumption. That paragraph disappeared in HCM 2010. And so we didn't change FreeVal because we had to deal with it somehow. So you could have a case where you enter on-ramp and then your output says ONR-B, on-ramp analyzed as basic segment. But it's actually not documented in the HCM 2010 that it should be done this way. It's HCM 2000. So it's just this little paragraph that disappeared.
In the HCS version of Freeway Facilities, you have an input segment type, and then when you go to results, it'll have an extra column showing the analysis segment type. So you may have inputted as a weave, but in a certain time period, you have to show up as a basic, like he's saying, where you have lane add and an on-ramp, or lane drop and an off-ramp. Those may show up as basic segments for analysis purposes. But again, those can only change from one 15-minute time period to the next.
So
Well, I guess we're
Yeah.
pretty much out of time. Everybody probably wants to get to lunch now. Is lunch being catered? Is that the deal, or?
Yes, I believe so. Roger?
Lunch is right outside the door.